So the next video on chapter 4 is going to be a quick introduction to uniform circular motion and just some of the terminology we're going to need. Okay, so first, what do we mean by uniform circular motion? Well, the circular part means that you're moving in a circle, not surprisingly. The uniform part means that you're moving in a circle at a constant speed. Note here, this is the constant speed, not a constant velocity. Because as you're moving around a circle, the direction is changing, which means your velocity is changing. But here, uniform means your speed is constant. Okay, so yes, so the direction of the velocity is constantly changing for an object in uniform circular motion, so it has to be accelerating. More than that in just a second. Okay, so some quick definitions, so some angular quantities. So if you have an object moving in a circle, so on the right here we've got a little circular arc length, so some circular path. It's actually convenient to talk about, right? So the radius is constant, so it's convenient to talk in terms of the angle. So the angle theta, and typically we measure theta in radians. So the arc length, so the total distance traveled, is actually the angle theta times the length of the radius r. And in fact, this is just how you define angles in radians. So, if we're going to talk about angles, it's convenient to talk about something called angular speed. And the angular speed omega, so this isn't a W, it's a lowercase Greek omega. And just similar to what we had with linear translational velocity, we just took a time derivative of the position. Similar thing here, we take a time derivative of the angle theta. So d theta dt gives us the angular speed omega. So we can use these two relationships and actually get a very handy relationship between the angular speed and the translational speed, right? So the speed v is the instantaneous speed v, is the time derivative of the distance traveled, s in this case, with respect to time. But we know s is equal to theta times r, so we need to take the time derivative of theta times r. We know r is constant, so since we're moving in a circle. So we pull out r from the derivative, and we have r times d theta dt, but remember d theta dt is just omega. So in general, for if you have an object moving in a circle, the instantaneous translational speed v is r times the angular speed omega. Okay, and then for centripetal acceleration, so once again we have an object traveling in a circle at constant speed, but if we look at the velocity, so here we start off at point A, we end up at point B, we draw in our velocity vectors, so we have some velocity at time 1, velocity at time 2. Notice that the length of those vectors are the same, but the direction is changing. So to calculate acceleration, we need to find the change in velocity, delta v. So we need to subtract v2 minus v1, which actually gives you this little green vector delta v. And notice that's actually pointing in towards the center of the circle. And we can use the fact that this is use some similar triangles, and we can find something called centripetal acceleration. So, and this is the acceleration of an object in uniform circular motion. Remember, we decided there had to be some acceleration since the direction of the velocity is changing. Notice that this is sometimes also called radial acceleration, since it's always directed along the radius. So, and we're going to use an a sub c for centripetal acceleration. Some books use an a sub r for radial acceleration also. And again, if you do some geometry with some similar triangles over here, you can show that the magnitude of this is the speed squared divided by the radius. And this is always in the radial direction, well actually pointing in. So r hat is a unit vector. Remember, hats are denoting unit vectors. It's a unit vector pointing along the radius. And since we have this minus sign, that means it's pointing in. And if we remember our relationship between v and omega, we do substitute that in and we can rearrange a little bit. We could also write this as minus omega squared r in the negative r hat direction. Okay, and the thing to remember about centripetal acceleration, so it always points in towards the center of the circle. And again, we aren't going to go over this quite yet, but this is actually still true even if you have non-uniform circular motion. So if you're still moving in a circle, but you're speeding up or slowing down, that would be non-uniform circular motion. And this relationship is still true for the radial component of the acceleration. Okay, and now just some quick related terminology. So if you have, in general, objects in periodic motion, so circular motion is an example of periodic motion. It's just motion that repeats. So for a circular motion, you're going round and round and round and round and round and round. So that's periodic motion. So the period, which we'll denote with a capital T, is the time for the motion to repeat. And I actually like the notation because the period is a time, so we use a T, but it's not any old time, it's a particular time, so it's a capital T. So it's just the time it takes for the motion to repeat. So if we're moving around in a circle, the period T, capital T, is the time for the object to make one complete revolution. Now, sometimes it's also convenient to talk about something called the frequency, F. So the frequency is just the reciprocal of the period. So the period is the time for one revolution. The frequency is the number of revolutions per time. So they're reciprocals of each other. So F is 1 over T, or T is 1 over F. And also another useful relationship. So if you have an object in uniform circular motion, it's easy to find the speed. Well, in general, speed is just the distance you traveled divided by the time it took. So if you're moving in a circle, a rather convenient distance is one complete revolution, or the circumference of the circle. And if that's what you use for the distance, then the time should be the time to go around once, which we defined as the period. So in general, in uniform circular motion, the speed of an object you can find as the circumference, 2 pi r, divided by the period, capital T.